Welcome to session 3. Please, Kate Curley and Kimberly Crowley, please take it over from me. Thank you.
Hi, everyone. Welcome to session 3, which is from cuff to cuffless and everything in between, new frontiers in BP monitoring and assessment. I'm Kate Curley, one of the moderators. I'm a family physician, and I work for the American Medical Association in Kimberly.
For this session, and I'm a biomedical engineer and team lead at the Center for Devices and Radiological Health at the FDA. Next slide, please. And our first presenter today is Dr. Marwa Abdallah. She's a cardiologist, a clinical researcher, and an associate professor of medicine at Columbia University, as well as also a co-chair for this workshop. She will be speaking about the contextual gaps and challenges in blood pressure measurement in the office and out of office blood pressure monitoring.
Thank you so much. Next slide, please. I have no disclosures. I am supported by the NHLBI. Thank you. As we all know, for some individuals, blood pressure in the office setting is not reflective of their usual blood pressure outside of the office setting. As such, the 2017 ACC/AHA guidelines have a 1A recommendation for out-of-office blood pressure measurements, either via ambulatory blood pressure monitoring or home BP monitoring. Next, please. Now, when we cross-classify office blood pressure with out-of-office blood pressure, we have 4 blood pressure phenotypes. 2 of these represent a mismatch, white coat hypertension, and the second is masked hypertension, which is defined as non-elevated office blood pressure with elevated out-of-office blood pressure, which has been associated with target organ damage and cardiovascular disease events. Next. Next slide. Next slide. Thank you. Ambulatory blood pressure is usually measured in the naturalistic environment, typically over a 24-hour period using an ambulatory blood pressure monitor or ABPM, which can identify these phenotypes as well as measure sleep in the 24-hour pattern of blood pressure. Now, ambulatory blood pressure has a stronger association with cardiovascular disease than office blood pressure. Next. However, we know that there are several limitations of ABPM, including poor patient tolerability from cuff inflation and sleep disruption. The device itself is expensive. It's usually placed at specialized centers with expertise. The device isn't readily available, and in fact, overall utilization of ABPM is low despite CMS reimbursement. Here's data from our group, which show that from 2007 to 2010, only 0.1% of Medicare beneficiaries actually had ABPM claims. Next. In contrast, home or self-measured blood pressure is more widely available, may be a more pragmatic approach in clinical practice. Obviously, we know that to do it properly requires a certain amount of training. It should be used using standardized protocol as well. And guidelines obviously suggest individuals perform 2 readings in the morning and 2 at night for at least 7 days. Although there is some data from our group showing that even 3 days of readings are acceptable, and obviously ensuring a validated device. Next. Thank you. There's some data showing that also home blood pressure monitoring may be more reliable than office blood pressure and ABPM and more strongly correlated with end organ damage. Again, here's data from our group using the Improving the Detection of Hypertension study, which is a community-based study of New York City adults without a history of hypertension who all underwent office blood pressure assessment, ambulatory blood pressure monitoring, and 2 weeks of home blood pressure monitoring. We compared the reliability of office blood pressure, which was conducted on 3 visits with 3 readings per visit. Blood pressure was measured by ABPM every 30 minutes over a 24-hour period, and blood pressure was measured by home blood pressure monitoring using a protocol of 2 readings in the morning and 2 evening readings over a week. And we examined the associations of each blood pressure measure with left ventricular mass index on 2D echo as a measure of target organ damage. Now, in the first table above, the interclass correlation coefficient was highest for home blood pressure as 0.94. In the table below, it shows the 3 separate models that we examined to determine associations with left ventricular mass index. Model 1 is an unadjusted model. Model 2 is adjusting for demographics, BMI, diabetes status, and Model 3 is a fully adjusted model that includes the covariates in Model 2, as well as the other blood pressure measures. So after multivariable adjustment, including for office blood pressure and awake ambulatory blood pressure, a 10 millimeter higher systolic and diastolic home blood pressure were associated with nearly 5 gram per meter squared higher left ventricular mass index. After adjustment for home blood pressure, neither office blood pressure or ambulatory blood pressure was actually associated with left ventricular mass index in the study. This may suggest that when blood pressure is assessed using guideline recommended approaches, home blood pressure monitoring may actually be superior to office and awake ABPM, and maybe that even ABPM may not be needed when you conduct office and home blood pressure monitoring. Next. However, as we know, next, there are certain limitations of home blood pressure monitoring. Unlike ABPM, most devices cannot measure blood pressure during sleep, although there are now some nocturnal home blood pressure devices, but those are not widely available. We know that home blood pressure monitoring is best with co-interventions. Automatic recordings and telehealth integration is not available in every single medical center and space. And obviously long-term patient adherence is challenging and reimbursement rates are low. Next. I think you missed a slide. There should be a slide before this. Backwards, please. Yeah, thank you. So which is superior, ABPM or home blood pressure monitoring? And that's one of the biggest unanswered questions. Which device is more associated with CVD events and or mortality? We conducted a systematic review of more than 1,000 articles and identified only 9 articles from 7 cohorts that examined whether blood pressure on ABPM or home blood pressure monitoring is more strongly associated with CVD events and mortality. And we found that when ambulatory blood pressure was adjusted for home blood pressure, systolic blood pressure on ABPM was associated with the outcomes of interest in 2 of 4 cohorts and 2 of 3 cohorts for diastolic blood pressure. When home blood pressure was adjusted for ambulatory blood pressure, systolic blood pressure on home blood pressure monitoring was associated with outcomes in 0 of 3 cohorts and only 1 of 2 cohorts for diastolic blood pressure. So clearly this remains an unanswered question given the small number of studies in the literature. Nonetheless, the 2017 ACC/AHA guidelines do suggest the following algorithm. For individuals who are untreated, the use of daytime ABPM is preferred with home blood pressure monitoring as an alternative, whereas for treated adults, home blood pressure monitoring is preferred with an alternative daytime ABPM. Next. Besides a lack of data on outcomes, values obtained using home versus ambulatory monitoring do not always agree. So we examined the agreement of ABPM and home blood pressure monitoring on masked hypertension using data from the IDH study. In our sample, the majority, next, 61% had masked hypertension only detected on ABPM. Next. Approximately 30% had masked hypertension detected on both ABPM and home blood pressure monitoring. Next. While a small minority, 9%, had masked hypertension that was detected only on home blood pressure monitoring, but not on ambulatory blood pressure monitoring. So I think these findings suggest that if you only use home blood pressure monitoring, you may misclassify many, if not the majority of individuals who have masked hypertension, as you're going to miss approximately 60% of those who were detected on ABPM. So as I mentioned earlier, masked hypertension is associated with CVD events and is missed in the office setting. So the use of home blood pressure alone may also fail to detect this phenotype. Next. Because masked hypertension is missed in the office, another critical research priority then is figuring out how best to screen for masked hypertension. We can't obviously screen everyone in the US with non-elevated office BP. That would be an estimated prevalence of about 17 million people. I've already discussed some of the limitations of both devices and their widespread implementation barriers. So really, is there a better approach to measure office blood pressure without the need to conduct ABPM, which would potentially be a paradigm shift in hypertension diagnosis and management? Next. So what is this new paradigm? What's proposed has been the use of unattended office blood pressure measurement, which refers to the use of an automated oscillometric device without a clinician present in the office to measure office blood pressure. Next. So unattended blood pressure measurement should ideally use a standardized protocol with a wait period followed by automated office blood pressure measurements without the clinician present in the room in order to eliminate the white coat effect and therefore white coat hypertension for some individuals. However, when you look at the data, there's a scarcity of high-quality data, with some showing no difference between unattended and attended office blood pressure, and others that unattended office blood pressure is lower than attended office blood pressure. Now, when you look at these studies, attended and unattended blood pressure measurements were often not performed within the same participant. An example of that would be the SPRINT trial, which did perform unattended blood pressure measurements, but were not done in the same participants, and there were differences across sites. Obviously, SPRINT was also not a priori designed to compare unattended with attended automated office blood pressure. Next. So in a recent systematic analysis of 12 studies, the mean systolic and diastolic blood pressure difference between unattended and attended blood pressure measurements was minus 3.66 and 1.67 millimeters of mercury, respectively. Now, although there's an interest in unattended office blood pressure, again, when you closely examine these studies in these meta-analyses, in addition to the fact that measurements were not performed within the same participant, so within individual indifferences cannot be determined, the few that did compare attended and unattended blood pressure within the same participants, many of these studies actually did not randomize the order of blood pressure measurements. And obviously the attended blood pressure was performed first. So thus, order effects and regression to the mean cannot be excluded. And further, within these same randomized studies, most did not compare office blood pressure to awake blood pressure on ABPM. Further, there's really few data with diverse populations included, and there still remains a critical research gap as to whether attended or unattended office blood pressure is closer to awake blood pressure on ABPM. Next. So what are the clinical implications of unattended blood pressure? So for the purpose of this slide, I'm going to walk you through, let's assume you're omniscient. You already know that the awake blood pressure, if you had conducted ABPM, is really the truth, and it correctly reflects an individual's blood pressure. So let's go through the first scenario. If attended office blood pressure when performed using proper technique is actually similar to awake blood pressure on ABPM, then there's no need to change our usual clinical practice. Now for scenario 2, if unattended office blood pressure is actually closer to awake blood pressure on ABPM when compared to attended office blood pressure, then we really should be using unattended office blood pressure. Our clinical workflow would have to change. Our patients would need to be instructed on how to self-measure blood pressure during office visits. We need to find time in an office space to have people sitting alone. In theory, the prevalence of white coat hypertension and MAST hypertension would be lower, and individuals would not be overtreated or undertreated, respectively. However, in the third example, again, we're still imagining the truth, that the patient has high awake blood pressure on ABPM. You also know the truth that their attended office blood pressure, if you had actually checked it, was also high. And it's actually closer in value to the awake blood pressure, meaning that this person you actually know truly has a diagnosis of sustained hypertension. Now, instead, you had this patient perform unattended office blood pressure, and for whatever reason, their unattended office blood pressure, maybe because of poor technique or otherwise, is mistakenly not high and has a value that's actually lower than what their true blood pressure should be. They would not meet the threshold for sustained hypertension. In this case, the likelihood of MAST hypertension then would increase. In this third scenario, individuals with sustained hypertension would now be converted to having MAST hypertension. This diagnosis would then be missed in the office if you just use unattended office blood pressure only. In effect, the patient would otherwise have been diagnosed as having sustained hypertension if you had conducted ABPM, and treatment may have been initiated. So in this case, unattended BP would actually cause more harm. And there are not many studies who've looked at what happens to the prevalence of MAST hypertension in these scenarios. Next. But what about sleep blood pressure? The sole reliance on office blood pressure, I think, ignores the impact of high sleep blood pressure on cardiovascular outcomes, particularly in Black adults. We found that the prevalence of MAST nighttime hypertension among individuals without a history of hypertension was particularly high in Black adults in the Jackson Heart Study. That's the figure on the left side. And with over 40% having high nighttime blood pressure versus 22% have high daytime blood pressure. So if these individuals were being seated in the office and just had an office blood pressure, they would not have been diagnosed at all, obviously. We also showed that nocturnal hypertension, defined as sleep systolic blood pressure of 120/70, is also associated with high cardiovascular disease events. This is there's a table on the right side, and in the table, the heart hazard ratio in Model 4, which is a fully adjusted model, the hazard ratio for CVD events associated with high sleep blood pressure was 2.07 in the fully adjusted model. Next. So high nighttime blood pressure has also been associated with cardiovascular disease events and mortality in other cohorts. That there's data from individual level meta-analysis. Here I present one from 13 population-based studies, over 11,000 individuals from Europe, Asia, and South America. Median age was 54, almost half were women, and the study had 13.8 years of follow-up data. And what they found that for each 20 millimeter higher nighttime systolic blood pressure was associated with all-cause mortality, and the multivariable adjusted hazard ratio was 1.23. In the same study, they also looked at CVD events, which was defined as cardiovascular mortality combined with non-fatal coronary events, heart failure, stroke. They found a similar association. Each 20 millimeter of mercury higher nighttime systolic blood pressure was associated with cardiovascular disease events. There, the multivariable adjusted hazard ratio was 1.16, and which did not change with further adjustment for 24-hour blood pressure. Next. So another gap and one of the main challenges in this field is obviously blood pressure thresholds and the chase to understand what modality provides the best estimate of true blood pressure. To quote the 2017 ACC guidelines, the precise relationships between office readings, ambulatory and home readings is unsettled. There's general agreement that office blood pressures are often higher than ambulatory and home blood pressures. And here I highlight from the guidelines the example that they provide with the differences in blood pressure thresholds for home blood pressure, daytime, sleep, and 24-hour ABPM at corresponding office blood pressure thresholds of 120 over 80, 130 over 80, and 140 over 90. As you can see, only for an office blood pressure threshold of 120 over 80 and 130 over 80, do you have the same threshold for home blood pressure and daytime ABPM, whereas that's not true at a threshold of 140 over 90, and this discrepancy actually increases with higher blood pressures. Obviously, nighttime blood pressure and 24-hour ABPM on the chart shows that they have their own separate blood pressure thresholds, which on a practical level leads to a lot of confusion for patients and clinicians alike when you're trying to compare office and out-of-office blood pressure. Next. So obviously the next gap to consider, and this is where I'll end, is with the introduction of continuous blood pressure monitoring. What does this mean in the context of establishing blood pressure thresholds? Will the same thresholds apply or should they even? Next slide, please. So in summary, I provide some key knowledge gaps and future opportunities. Some key gaps include defining uniform blood pressure thresholds across office and out-of-office blood pressure measurements, and obviously with new devices. Can we improve upon office blood pressure measurement? It's self-measured blood pressure, but just in a different environmental context. I have not spoken to the implementation barriers at length, but obviously the impact of structural level factors is a key gap. What are some future opportunities? I think, can we totally disrupt the concept of office blood pressure and only rely on out-of-office blood pressure? I do think that unattended office blood pressure may actually be a gateway for improving patient education and engagement in self-home blood pressure measurement and thinking about the environmental context for which we start to engage individuals for self blood pressure measurement. A second, future opportunities, what are the reliability and validation of continuous blood pressure devices? I know there are many people who will speak about this later on, including what are the minimum number of readings are needed to define a complete reading in these new devices. And lastly, can we reliably assess nocturnal blood pressure for more than a 24 to 48 hour period? There are many new devices in the market, but can we measure blood pressure without disturbing sleep? Thank you so much.
Thank you so much, Dr. Abdallah. Next up, I believe we have Dr. Ramakrishna Makamala talking to us all about cuffless blood pressure measurement. Go ahead and take it away.
Next slide, please. Okay, good afternoon. Thank you to the chairs and organizers for the invitation to participate in this important workshop. I've studied cuffless blood pressure measurement for more than a decade now. And I'm going to tell you where we actually stand at present with this technology. And before I begin, I should mention that I have NIH funding and patents on cuffless blood pressure technology that is different from the methods that I'll focus on today. So next, please. Okay, so here are the conventional methods for non-invasive measurement of blood pressure. Amongst these methods, oscillometry in the form of automatic arm cuff devices has emerged as the most widely used method by a significant extent. This is 50-year-old technology. It's easiest to use, it's inexpensive, and closest in accuracy to the standard manual auscultatory method. However, as with all conventional methods, oscillometry requires an inflatable cuff and is not readily available and cumbersome to use. Next. So many want to eliminate the cuff from blood pressure measurement, and cuffless blood pressure measurement has now become a field. Studies are increasingly appearing in the literature, as shown in the upper left, and several wearable devices are now cleared by the FDA as well as the European Commission, as shown on the right. A comprehensive review of the flurry of activity can be found in the lower left. Next, please. So most of the studies, and likely all of the regulatory cleared devices, employ pulse wave analysis with or without pulse arrival time. So pulse wave analysis methods typically measure a photoplethysmography or PPG waveform, which indicates small vessel blood volume oscillations, or a tonometry waveform, which indicates net peripheral artery forces. So neither waveform directly indicates blood pressure. So these methods will then extract features from the waveform and map or calibrate these features to blood pressure values using machine learning. Pulse wave analysis with pulse arrival time methods also record an ECG waveform to extract pulse arrival time as the time delay between the ECG and hemodynamic waveforms, and possibly other features. And as shown in the gold box, these methods require periodic measurement with an arm cuff device as part of the calibration procedure, or use only demographic information such as age, biological sex, and BMI for less reliable calibration. And therefore, and the most important thing to understand, is that the sole purpose of these devices is to measure blood pressure changes in a person relative to the calibration, rather than measuring the absolute blood pressure level. Next, please. So I think it's important to note that these methods are not supported by generally accepted physiological principles. So as just one example, a basic physiological model to the left indicates that PPG changes are equal to the product of small vessel compliance and blood pressure changes. Small vessel compliance is modulated by smooth muscle contraction and can therefore vary independently of blood pressure. So if you look to the right, there are data showing that as a consequence, changes in blood pressure induced by various interventions have little relationship with the induced change in PPG amplitude. So you can see that mental arithmetic, which is primarily a cardiac intervention, increases both blood pressure and the PPG amplitude, whereas cold pressure, which is a vascular intervention, increases blood pressure by a similar amount, but decreases the PPG amplitude via a reduction in small vessel compliance. Next slide, please. So even so, numerous studies claim that pulse wave analysis methods are accurate. However, many of the studies are actually problematic. So firstly, results in published papers are often presented incorrectly. So we performed computer studies to simulate cuffless blood pressure measurements with zero correlation to reference cuff blood pressure measurements, and then presented the results like in many papers. That's what's shown in gray. The results show impressive correlation of a cuff calibrated method with cuff blood pressure. However, when the data are presented correctly, as the change in the cuffless blood pressure relative to the calibration versus the change in cuff blood pressure relative to the calibration, we see the true lack of correlation in the lower left. Secondly, the testing protocol employed in many studies often do not include blood pressure changes, and blood pressure changes, again, are what pulse wave analysis methods measure. And most notably, a number of studies have employed the AMI-ESH ISO Universal Standard for testing automatic cuff devices to assess pulse wave analysis methods. However, this standard is not applicable to pulse wave analysis methods because it does not include the necessary blood pressure changes. Studies of cuff-calibrated pulse wave analysis methods without any blood pressure changes can be simply dismissed. And thirdly, and perhaps most importantly, many studies do not include comparisons to fair baseline models as shown in the lower right. So pulse wave analysis methods again compute blood pressure from a hemodynamic waveform measurement and a non-waveform information such as the cuff blood pressure for calibration, age, sex, and BMI. It is well known that this other information, the other non-waveform information, correlates with the blood pressure for measurement. So the methods must therefore be compared to baseline models in which blood pressure is computed only from the non-waveform information to determine if the method is worth using or not. A pulse wave analysis device is superfluous if the waveform that is measuring does not offer any value to blood pressure measurement accuracy. Next slide. So some studies of pulse wave analysis devices with company involvement appear to be properly done and show remarkable results. So to the left are results from one study of a demographic calibrated wrist tonometry device against invasive blood pressure. And you can see the correlation is strong, especially considering that demographic calibration was employed. To the right are results from another study of a cuff-calibrated wrist PPG device against 24-hour ABPM. The R-squared values are 0.95 to 0.99. I'm talking R-squared, not R. Note that cuff blood pressure measurements have significant error in plotting the measurements of one cuff device versus another cuff device would not yield this R-squared level. Next, please. So as Stephen mentioned, a Microsoft research team recently published a comprehensive study to determine if pulse wave analysis methods can actually track blood pressure changes. They designed a practical yet informative study and included over 1,000 diverse subjects. They built wrist devices to measure PPG, tonometry, and ECG waveforms. And they then explored an array of machine learning algorithms to develop models for computing blood pressure from waveform features and non-waveform information, such as the cuff blood pressure measurement for calibration and the time of day. Yes, the time of day to help with diurnal blood pressure changes. Crucially, they created fair baseline models to compute blood pressure from the non-waveform information alone, as shown on the lower left. And they found that the waveform feature models were only able to yield slightly lower blood pressure errors against reference cuff devices than the baseline models, as shown on the lower right. Their results therefore indicate that pulse wave analysis methods offer essentially no value in blood pressure monitoring. Next, please. So the Microsoft research project should be regarded as an authoritative study of pulse wave analysis methods for the following reasons. An elite research team performed an unbiased study of cuffless blood pressure without financial or publishing concerns. The study cost millions of dollars. The study constituted an exhaustive assessment of wrist pulse wave analysis methods with high similarity to the regulatory cleared wrist devices that I showed earlier. The team found that these methods offered no value in measuring blood pressure over fair baseline models. This means that they did not work at all, zero. The team is offering their data for free to the public, and the team evidently quit cuffless blood pressure research following their study. Next, please. A few studies of the latest FDA-cleared pulse wave analysis devices have shown that they perform similarly to baseline models. To the left are results of a calibrated Garmin device showing that it yielded a systolic blood pressure error of 8.7 millimeter of mercury against cuff blood pressure, whereas a baseline model that computed blood pressure from only demographic information produced a slightly higher error of 9.4 millimeter of mercury. To the right are results of a demographic calibrated tonometry device against invasive blood pressure in infants. Although results from baseline models were not provided, the correlation plots indicate that body weight alone could have estimated the blood pressure fairly well here. Next slide, please. Because of the lack of convincing validation data, the European Society of Hypertension recommends that cuffless blood pressure measurement devices should not be used in clinical practice. Next slide, please. So I would like to at least mention that concepts for cuffless and calibration-free, that is truly cuffless blood pressure monitoring, have been proposed. And none of these far less investigated methods would be as convenient as pulse wave analysis devices after cuff calibration, but they or other future methods might eventually be shown to yield sufficient blood pressure accuracy without using a cuff. Next slide, please. So in summary, the field of cuffless blood pressure can only be understood by taking a deep dive. Popular cuffless devices have not been proven to offer significant value in blood pressure measurement accuracy up to now. So if you have any doubts, consider this. Blood pressure is by far the most important physiological variable for a consumer device to be able to monitor. If pulse wave analysis methods really worked, then why don't the leading companies in the world with elite machine learning teams and vast resources offer cuffless blood pressure monitoring? Future technology development work is worthwhile and needed to realize the dream of cuffless blood pressure measurement. Thank you.
Dr. Kamala, apologies. Our next presenter is Dr. Tammy Brady, who is a professor of pediatrics and epidemiology and medical director of pediatric hypertension program at Johns Hopkins University. She will be talking about the best practices for blood pressure validation.
Thank you very much, Kimberly. It's my pleasure to be here. Thank you very much to the organizers for inviting me. And today I'm going to be talking to you about something that I'm very passionate about. So in addition to being passionate about blood pressure measurement, I'm passionate about device validation. And related to that, I'm about to finish out my third term as the co-chair of the AME, or the Association for the Advancement of Medical Instrumentation Sphygmomanometer Committee, which helps develop the validation protocols. And I'm also co-chair of the AMA Validated Device Listing Committee, along with Dr. Jordan Cohen. Next slide, please. So there are a number of validation protocols that have been available across the last several decades. You can see that this is the availability of validation protocols for device manufacturers to test that their device is clinically accurate, has been available since the 80s. There have been a variety of different organizations, some professional organizations and professional societies that have come up with different protocols. And particularly with AMA ISO, there's been multiple iterations of protocols to improve upon them. The most recent iteration was published in 2018, and this has been largely thought of as the universal standard. This is currently being updated as we speak, and a newer version will likely be out in the next year or so. Next slide. And so I'm going to be given the task to go over some of these validation practices, which these documents are quite dense, but I'm going to do my best to go through what some of the key concepts are. So most of us think about, when we think about validation standards, we're thinking about cuff devices that provide intermittent blood pressure measurements. And we in the AIMI world call this the -2 standard. Next slide. Next slide, please. So there are several other standards that we work on the AIMI committee. There is the -3 standard, which addresses blood pressure devices that provide continuous cuffless measurement. I will go through that in a little bit later on. There is the -4 standard, which is in progress, which is intended for use for devices in patient transport. Next slide. There is the -5 standard, which allows us to test repeatability and reproducibility of simulators used for testing of automated non-invasive sphygmomanometers. And then there's the -7 standard, which is in production or in progress, which will help us test the intermittent cuffless measurement devices. This has been going on for over a year. It's been a very active group, and it is hopeful that we will have at least a draft standard of this by the end of February 2025. Next slide. Oh, yeah, I have some animation. Sorry, for a couple of those. So we're going to talk first about the -2 standard. Next slide. Go 2 slides down. One more. Yes, here. So to get us started, I just wanted to give us some definitions to really help us set the stage. So in doing validation testing to determine if a device is accurate, you have your device under test or the sphygmomanometer under test, and that needs to be tested against a reference standard. In the validation protocols, there are 2 potential reference standards for use. An invasive one using arterial line blood pressures, or a non-invasive one, which is an auscultatory measurement that is either obtained by the mercury device or an aneroid device with a specific amount of accuracy. These auscultatory measurements need to use a 2-piece cuff that has a bladder that meets very specific dimensions, which you can see delineated on the slide. This testing is typically done in either a general population, or it will also be done in a special population. So a special population is one in whom there's either a theoretical chance or clinical evidence that the device will act differently in that population. And the general population is what you would expect. It's adult comers over 12 years of age who are either untreated or treated as hypertensive or normotensive or hypertensive. Again, untreated or treated. Next slide. So for a general population study, like I said, you can either have an auscultatory reference where you would need to have at least 85 subjects enrolled, or you can have an invasive reference, which you would have at least 15 subjects enrolled. The population that you're studying needs to be above 12 years of age. You need to be at least 30% male sex and 30% female sex. And then the percent of your reference readings need to fit a specific blood pressure distribution, which you can see delineated in the table to the right. And this is so that we can determine whether or not the device performs sufficiently well across a wide range of blood pressure values. In addition to fulfilling these requirements, each of the cuffs that come with the device need to be tested and need to have a specific number of individuals tested using those cuffs. And then the entire cuff range you need to make sure that the cuff range is tested. And I'll show you what I mean in the next slides. Next, please. So when we think about a device, the cuff is integral to the device. And many devices will come with several different cuffs. Next slide. And so this figure is something that was shown earlier today. And this is looking at all of the devices that were available on the AMA BDL website. So you can see on the left the various devices and the device names. And to the right with the rectangles, you'll see what cuffs are available with each device. And then you can see, using the reference along the top, what the arm circumference range is appropriate for each one of those cuffs. So to go through what I was describing earlier in terms of the number tested per cuff and testing across the cuff range. I'm going to use two examples. Next slide, or yeah, next. So we're going to use this example here, next. And you can see that this device comes with 3 different cuffs, and that the cuffs, next slide, have a limb size distribution of 14 to 42 centimeters, and they achieve that distribution using 3 different cuffs. Next slide. And again. Now this cuff, this device comes with 4 different cuffs, and these 4 different cuffs accommodate a different group or different limb size distribution. It accommodates people who have an arm circumference anywhere between 20 and 55 centimeters. Next slide. So when manufacturers are testing either one of those cuffs, then they have to figure out how many individuals need to be tested per cuff. So on this slide, you'll see on the top, there are 3 greenish rectangles, and that's supposed to refer to the device that's delineated in red. And then the 4 bluish rectangles are for the device delineated in blue. And so when you have a cuff, go back. So when you have a cuff that is 12 centimeters or less, there's a very specific formula that you use to determine how many people need to be tested in that cuff. And when you have larger cuffs, like you see with the yellow star, you will have a different formula to determine how many individuals need to be tested. So this will tell you how many per cuff, but you need to also, like I said earlier, make sure that there are that each one of the cuffs is tested across that cuff range. Next slide. So, I'm sorry. So this will, using those formulas, you will see that the first cuff family, there are 12 and 15 individuals that need to be tested in each of the cuffs. And then you can see in the cuff family where there are 4, for the larger cuff, there's a much larger number of individuals that need to be tested. Next slide. So, in addition, each, for the cuffs that are the smaller size, so 12 centimeters or less, it's not just enough to have 12 people, per se, in that first cuff that you see on the upper left, but half of the, or 40% of the subjects need to be tested within the upper half of the specified range, and half of them, 40% of them need to be tested in the other half. And so, as an example, you can see the first cuff, 5 of them at least have to be tested in the lower half, and 5 have to be tested in the upper half. For the larger cuffs, or the ones that are 16 centimeters or greater, there's even greater requirements. At least 20% of the subjects in this who are allocated to that cuff to be tested, so 30 in this example, need to be in each one of the quartiles of the arm circumference that is accommodated by that cuff. And then at least 10% of the subjects need to be in the upper octile and the lower octile of that cuff range. Next slide. So once you've gotten your patient population, your study population, then you're moving on to the actual testing. So the testing that occurs is exactly the patient preparation, and the actual measurement procedure is the same as our usual clinical practice guidelines. In our current AIMI protocol, we use what's called the same arm sequential method. And what that means is that the cuff is, the reference cuff is put on one of the arms. You have 2 independent observers. They use a double-headed stethoscope. They simultaneously will figure out or determine what the K1 and the K5 is, which is associated with the systolic and diastolic blood pressure. And then once they get their reference measurements, the cuff is removed, and then the device, along with the device cuff, is put on that same arm, and they get measurements with the reference device or the device under test. Any one of the paired systolic diastolic blood pressures that differ than more than 4 millimeters of mercury is excluded. And you need ultimately, at the end of the day, at least 255 paired measurements. There are 2 criteria that need to be passed. The first criterion deals with individual readings, and then the second criterion deals with readings within individual subjects. So criterion 1, you take those 255 paired measurements, and you look at the mean blood pressure difference for all. So the test measurement minus the reference measurement. And overall, that needs to have a difference of less than or equal to 5 millimeters of mercury, with no more than 8 millimeters of mercury as a standard deviation. Then for criteria 2, you take 85 average blood pressure differences, and then you determine what that average difference is. And then on the table I'll show you on the next slide, you're able to determine what the allowable standard deviation is, and then that will allow you to know whether or not your device can pass. In this example, when they were doing that criterion 2, you can advance one more time. They came up with a mean blood pressure difference of 4.2 millimeters of mercury, which then allowed them to have no more than 5.49 millimeters of mercury standard deviation, and so then that would be used to interpret what the results were. If you could advance twice, please. So that's how. So that's overall how you conduct validation testing for a device with a cuff using the auscultatory reference in a general population. If you have a device that has additional intended use, such as exercise stress testing or ABPM, there are separate requirements. And then certainly I did not review what needs to happen for an invasive reference study. Next slide. So next, one of the things that I'm very interested in as a pediatric nephrologist are some of these special populations. And so these are 3 populations in whom devices are likely to act or perform differently. And so they have been designated as a special population, meaning that there is additional testing that needs to be done in these populations to ensure that they're accurate. Next slide. And so what this means is that if you want to have a device that, next slide, is tested or is designated for an infant, next slide, then you can see, well, first here, you can see that these are the differences in terms of testing requirements for each of these 3 special populations. For infants who are anywhere from birth up to less than 3 years of age, the will be different in future iterations. You need 18 subjects. You can see that there are very specific requirements regarding weight and age. There's no BP, gender, or limb size distribution requirements, and there's very simplistic analysis that is done. There's only one criteria. For children who are 3 to 12 years of age, you can use an invasive reference or an auscultatory reference. You can do the entire testing in 85 kids, or you can do a general population study in which there are 50 general population participants above 12 years of age and 35 children for a total of 85 population. Or you can do 35 a study in 35 children as a special population after 85 participants have completed and passed a general population study. And then for pregnant women, the requirements in the AMI standard, AMI ISO standard, are that you can do testing invasive or auscultatory in 85 pregnant women or in 45 women as a special population after 85% general population study has been completed. Notably, for pregnant women in the 2nd and 3rd trimester, a third of the women who are included in whichever study you do need to have various blood pressure requirements of having either proteinuria or no proteinuria. Next slide. So that was the -2 standard. So I'm going to go briefly over the other standards. Can you do the next slide? So until 2022, there were no standards for AMI ISO standards, I should say, for cuffless devices. So many manufacturers use the -2 standard for this. And as we just heard, that was not necessarily appropriate. Next slide. So what cuffless devices do that give continuous measurements, and these are devices, and this is important to think about in terms of the more, like the watches and the rings that we've been hearing about that are coming our way. These devices that give continuous measurements provide beat-to-beat measurements and give you an output frequently. So 1 or more outputs every 30 seconds. This, because of the frequency of the output, requires an invasive reference. These devices can provide either trend data, which I think of as delta blood pressure, so the change in blood pressure, or it gives you an output that is meant to be an estimated blood pressure. In the standard, this is designated as type T and type A. Now, one thing that is specifically in the standard, which I think is important for all of us to know, is that users of these continuous automated cuffless devices could be misled to think that the values displayed on the screen are intended to be absolutely accurate, when in reality they are not. This document does not cover usability study that would be required to address this matter. Next slide. So for the type A, you need to determine if it gives you an accurate blood pressure, as well as does it give stable measurements and give you good blood pressure changes, whereas the ones that provide trend data or type T only require the last two of those performance assessments. Next slide. And then next. So I'll briefly go through this. So again, this needs to have an invasive reference, similar age sex distribution. There is a requirement for an age distribution to recognizing that as with older individuals, there's more arterial stiffness and these devices may act differently. So there is an age requirement that needs to be fulfilled. And there is a different blood pressure distribution because many of these devices are intended to be used in ICUs or in operating rooms where there could be bigger swings in blood pressure. So the blood pressure distribution is different to reflect that. Next slide. There's no required age distribution when being tested in children under 12. For those under 1 year of age, there is an age and a weight distribution that needs to be fulfilled. Next slide. And actually, let's just go past that one and the next one. And we'll go for time. One more. After that. No, keep going. Yes. So the one thing I did want to highlight for the continuous blood pressure devices, the standard requires that the paired values be less than or equal to 6 millimeters of mercury with a standard deviation of less than or equal to 10 millimeters mercury. Next slide. Which is very different than what is required for the cuff devices, where you can see what the performance standards are here. Next slide. So that was really focusing on the accuracy of blood pressure. And in terms of stability and blood pressure changes, there's additional testing. Next slide. And what the standard goes through is that these devices need to have specific things that tell you how they perform immediately post-calibration. Next slide. In different device positions, after inducing a blood pressure change, and then before those devices get recalibrated. So all of those things are handled in the standard. Next slide. So what about how we test devices that give you intermittent cuffless blood pressure measurements? And so this is something, again, I said, this is in progress. These devices are different than the continuous ones because these give you an output less frequently, so more than every 30 seconds, or upon when the user actuates it, pushes a button to give you a measurement. Next slide. So as we're developing the standard, we are thinking about, and we're developing the standard to address 6 potential and or existing devices on the market. So many of these devices, as was just described in the earlier presentation, require some sort of initialization and calibration. So many of them require personal information like demographics or metrics. And many of them require initialization with a cuff blood pressure, meaning you have to input all of your demographics and you have to measure your blood pressure with the cuff, input it into the device, the cuffless device, and all that information is used along with other methods like pulse wave analysis and pulse wave velocity to provide you with output. And so you can, so the 6 different types are the ones that don't require any initialization of personal information, considered to be plug and play devices. There are ones that, and then more frequently you can see here, the ones that require cuff blood pressure, does not require personal information, and either provides you an absolute blood pressure in millimeters of mercury, or it tracks blood pressure, just like I described earlier, providing more of a change in blood pressure. Next slide. So as we have been developing these standards, there are things that we've been thinking about. Some of them are highlighted here, which is the math document that was just shared, which is the ESH recommendations and things that we might want to consider for validation of cuffless intermittent devices. Next slide. So things that are being considered, thinking about how do we test static, absolute blood pressure accuracy? How do we test for hydrostatic pressure effect robustness? How do we test the effectiveness of blood pressure decreasing? And is it accurate when the blood pressure does decrease? Next slide. We're thinking about how do we test it when we're awake and asleep, the blood pressure change accuracy with position. When blood pressure exercise tests, if that's something we want to consider to help increase blood pressure and see if it's accurate with increasing blood pressure. And then seeing how the cuff, how the device is accurate over time the further it gets away from the initial cuff calibration. Next slide. So there are many blood pressure measuring devices available in the market. However, many people don't recognize that less than 20% of them have ever been subjected to a validation testing. So you can put your device on the market, even if it's never been undergone a validation testing. And of the ones that have published validation studies, there are protocol violations in a third of those. Next slide. And so I get people asking me all the time, but what about an FDA approved device? And one thing I just want to be clear about is that the FDA does not approve blood pressure devices, they clear them. So approval generally only applies to high-risk medical devices, and blood pressure devices are not sufficiently high risk. And so they get cleared through the 510(k) pathway. Next slide. And so a cleared device is one that is at least as safe and effective, that is substantially equivalent to a legally marketed device prior to May 1976. And again, clearance is speaking to substantial equivalence, not necessarily clinical testing of the new device. The predicate device needs to have been tested, but the new device does not necessarily need to be tested if it was deemed to be substantially equivalent. Next slide. And I think we're going to skip this one and the next one. Keep going. And then one more. Okay. So again, devices can be cleared without they themselves undergoing separate validation testing if the manufacturer claims substantial equivalence of the predicate device. Next slide. We're going to skip. Yeah, one more. So let's skip to the summary slide. One more. Okay. So in summary, there are multiple validation protocols available for testing numerous devices intended to measure blood pressure. They're very complex, and they're specific to make sure that they're accurate across diverse population and intended uses. Very few devices for sale have been tested for accuracy, and devices can receive FDA clearance if they're substantially equivalent. Next slide. And so with technology evolving quickly, these new tech innovations require innovative approaches by regulators, societies, and clinicians to make sure they're accurate, to make sure that those who are using them are educated on how they're used, thinking about how we can integrate them into clinical care. And so one thing to think about is how can we get all of those stakeholders to collaborate more closely to keep in step. Next slide. And then one thing we constantly have to think about when we're talking about validation standards is that really pertains to accuracy in a standardized research setting. It doesn't address how the devices perform in optimal settings. So what's missing is when you have a validated device, we don't know how it performs in the real world with typical use, and we don't really know how those measurements predict or associate with outcomes. Next slide. One thing that I found particularly interesting is as we were talking about some of the limitations to these cuffless devices, particularly how they don't really perform well during sleep, and thinking about what we need to do to test them during sleep, one thing to highlight is ABPMs are never tested during sleep. And some of those same hydrostatic effects may be at play with ABPM measurements. So how can we improve it and increase the consistency between the protocols? And then I think my last slide is next. And so, with those additional testing requirements for special populations, one of the downstream effects is that these populations then tend to not have as many devices available for use, and with children and pregnant women being particularly vulnerable. So we need to think about this and think about other innovative ways in which we can test and make sure these devices are accurate in those populations without leaving them out of many studies. And that is it. Next slide is my last slide. Thank you very much for your attention.
Thank you so much, Dr. Brady. We'll hand it over to almost Dr. Hillary Wall from CDC's Million Hertz.
All right, thanks a bunch, Kate. If we can go to the next slide. Great. So Hillary Wall, I'm here to talk to you about using big data for hypertension clinical decision making. And if we go to the next slide, I have no disclosures. I am going to mention some sort of trade names, not for endorsement, just using them for identification and examples. Next slide. So again, I was asked to give a talk about using big data for hypertension clinical decision making and some of the challenges and opportunities that there are in that field. I'm not a clinician. I am an epidemiologist by training, and so that's really the lens through which I'm looking through. But I also work with a lot of clinicians, especially community health centers, as they dig deep into their electronic health record data for quality improvement purposes in particular, and impacts that might have on clinical quality measures. So I'm going to hit sort of a whole bunch of topics here today, but I'm going to start a little bit with public health surveillance because that's where I come from, and our work using electronic electronic health record data for public health surveillance has actually provided us an opportunity to sort of look under the hood and see how the sausage is made with regard to electronic health record data and all of their sort of beautiful messiness that they bring. So next slide. Quickly, I just want to start, just in case you weren't aware, in the United States, the National Health and Nutrition Examination Survey is essentially our only surveillance data source for hypertension prevalence and blood pressure control. There are other data sources that get at sort of self-reported hypertension prevalence, but this is really our only data source that gives us hypertension and blood pressure control. However, it's considered a gold standard, but however, there's challenges with it, just like any data source, right? It's very expensive to maintain. It's not very timely. You're not getting real-time data from it in any way, shape, or form. And if you're a state or local health department, you're really not able to get subnational estimates from NHANES. And what we had the misfortune of finding out when the COVID-19 pandemic hit, it is not pandemic proof. When the country shut down, NHANES data collections shut down, and frankly has been disrupted in different ways, sort of inconsistently over the last 5 years. And it's only next year when their regular data collection cycles will begin again. So for 5 years, we've had not great estimates for blood pressure control, and that's a problem. So if we go to the next slide, but you know, the challenge when you have something called a gold standard, people aren't very quick to look for an alternative. Can we go to the next slide, please? So they're not quick to go to an alternative, and they're not quick to think outside of the box of how else we might get to those indicators that I mentioned. But back in 2010, 2011, when I heard about meaningful use, and I'm sure all the clinicians on the call are groaning right now, but when I heard about meaningful use, yes, I was happy it was going to improve efficiency and patient outcomes potentially, but I just was salivating over the huge volume of data that we would be sitting on top of. And yes, it was going to be messy and we needed to figure out methods for it, but this was a huge opportunity in my mind. And so I started squawking to anyone who had dollars and decision-making capability at CDC. And eventually we did get to the point where we were using EHR data for surveillance. So if we can go to the next slide. I certainly was not the only person who was thinking about electronic health record data for surveillance and other purposes. You can see on the left, especially public health jurisdictions that can't benefit from NHANES were thinking, what can I do at the municipality level in New York City and Denver? What can I do at the state level in Massachusetts to really use electronic health record data to answer questions that I have about serious health conditions? HRSA has been collecting their uniform data system for years from community health centers. It's really a programmatic database, but even that has been collecting routinely clinical quality measures data. It's allowed our nation to really look at how are we doing from a safety net provider perspective, and that's been morphing and changing over time as well. I'll talk a little bit about that. We also have health center controlled networks and health information exchanges that really aggregate data that then can be used for different purposes, quality improvement, performance measurement, etc. And we have research networks like PCORnet. And all of these folks who came before what CDC launched helped inform what we call our multi-state EHR-based network for disease surveillance, or MENS. And you're going to hear me talk about this. And again, the lessons that we've learned by being epidemiologists and digging into the very micro level details of this particular surveillance system can absolutely be applied to clinical decision making. So that's what I want to share. But let's look at what are some tools for clinical decision making. Next slide. I'm going to go through these pretty quickly. Next slide. Thank you. So first, quality improvement run charts. If you're doing continuous quality improvement, this is one way that you can monitor your progress there, usually using a longitudinal performance measure, a clinical quality measure, to really see how quality improvement changes have impacted the performance on something like blood pressure control. Next slide. You can also be using clinical quality measure dashboards, or just dashboards in general. And thanks to the AMA folks who let me use this particular slide. Here you can see we've got our outcome measure of interest, and then also some process measures that are related. And then here we've got, you dig down one more layer, what patients are falling out of the numerator on our performance measures. We can look at a registry to figure out who might need additional clinical attention. And then our next slide. we can look at either pre-visit or at the point of care, what's going on with that individual patient, and hopefully some of their longitudinal data on blood pressure. Next slide. But so any of those clinical decision-making tools that I just showed you, and many others, your clinical decision supports, your little triggers that go off in your electronic health record, they really all rely on what it is that triggers hypertension or blood pressure control in our favorite tool of, our choosing. And I can hear you all saying, it's ICD-10 codes, Hillary, obviously. And if you said that to me, I would say, well, yes, you're partially right. ICD-10 codes certainly can be used to trigger hypertension and can be used to build sort of blood pressure control measures. But I would say you're only partially right. If we go to the next slide, what I and many researchers in the field have come to understand is that when you really dig into electronic health record data related to hypertension, you start seeing non-trivial numbers of patients who have not been given a diagnosis code, have not been given an ICD-10 code, but they have, can you go back a slide, please? But they have multiple elevated blood pressure readings. And so we've sort of, this is like potentially undiagnosed hypertension in electronic health records. And Million Hearts, my program, has really dubbed this like hiding in plain sight. Because if you just sort of look for folks, you're going to start finding other patients that potentially have hypertension. And you can see here, Mike Raycotts has published on this. Heather Johnson has published on this. We've published on work that we've done specifically with community health centers to really dig into the micro level details. Kaiser's published on this both in non-pregnant populations and pregnant populations as well with hypertension. And so these are just some of my publications that are my favorites in this space, but there are many others as well. Let's go to the next slide. And what this is really coming down to is developing a hypertension phenotype using electronic health record data. And so, yes, of course, ICD-10 codes and ICD-10-I10 essential hypertension, that is what's used most commonly in our clinical quality measures and other related conditions, other related tools, excuse me. But might you, for your purposes, for your healthcare settings purposes, might you want to expand the ICD-10 codes that you're looking at? We heard Jordy talk about like hypertensive CKD. Might we want to look at that in some of our tools? Do you know what ICD-10 codes are actually being used to build the data visualizations that you're seeing? Now, many of the people on this call are hypertension researchers, and so you're very involved in your data, but I think your, sort of everyday clinician might not be as involved in the nuts and bolts of their data visualizations and their clinical decision-making tools. So these are just some considerations from an ICD-10 perspective, but I would also encourage folks to think about looking for patients that are on an antihypertensive medication. And I hear you, they're used for off-label reasons. We looked at that in that men's surveillance system I talked about, and it actually happened much less frequently than we had anticipated. So that's something to consider. I would absolutely consider using 2 or more elevated blood pressure values, but you have to think about what threshold you use. Do you just look at 130/80 or 140/90? You might want to start looking at higher blood pressure values because you have more confidence that those people likely have hypertension. Are you just using office blood pressure values? Are you thinking about using self-measured blood pressure monitoring values? AOBP if it's available to you, and then also some healthcare settings used to be more pertinent, but they take into consideration whether hypertension is written in the clinical notes. So all of these sort of data elements could be used to build a hypertension phenotype. What does a patient with hypertension look like from an electronic health record perspective? Next slide. You can do the same thing with blood pressure control, lots of different considerations. Are you using office blood pressure values? Which one? If there are multiple values in one day, you need to make a decision about how you're handling those. Are you dropping the first one? Are you averaging them all? Are you taking the lowest systolic and the lowest diastolic from 2 different measures and putting them together? That's what our clinical quality measures do, CMS 165, NQF 18. So there's lots of different decision points in there. And do you know what decision points have been made when you're looking at things like a blood pressure control report? SMBP, same thing. How are you handling those values? What if a patient brings in their values written down on paper? Are you using those the same way you might if they were transmitted electronically? How are you handling SMBP or RPM in the pregnancy and postpartum population? AOBP, same kinds of things. And then future technologies, these are things that as people are developing future technologies, I wish that when they got to the FDA clearance point, they would start saying, okay, let's assume I'm going to get FDA clearance. What do we need to do to really implement this broadly in the clinical settings in the United States? Like, these are the things, these are considerations that I wish device manufacturers would keep in mind. Next slide. So a lot of the challenges and like how you figure out whether or not things have been done, these are mapping issues, okay? And this gets like really sort of informatics heavy, but it's also not very well explored in the published literature. This is one example that we looked at those sort of meaningful use, the Medicare EHR incentive program data from physicians only who reported on NQF-18, which is controlling high blood pressure. The bottom two, if you look at 2014, the data on the right, the bottom two pieces of the column are just like how they performed. The top two pieces are what I want to point out. 4.4% of physicians reported they had 0 patients with blood pressure control. So of their patients with hypertension, no one had their blood pressure under 140/90. And then another 12% reported that they had 0 patients with hypertension. And these are physicians who chose to report on this measure. So that seemed really strange to us that you had this big portion of physicians claiming things, you know, on the opposite ends of the spectrum. So I think that what we decided was this was really a mapping issue, and those clinicians needed to work with their electronic health record providers to fix whatever issue they had. They weren't, wherever they were entering blood pressure into their interface, their EHR interface, wasn't making it to where it was being reported out. Next slide. So you all are likely familiar with the 5 rights of clinical decision support. You've got the right information going to the right person in the right format through the right channel at the right time. And I think when it comes to the right information, some of that has to do with data validation. And I'm not going to dive deeply into this, but we have a publication that I included on this slide where we really dug very, very deeply and went down a validation rabbit hole for that MENS system that I talked about. And when you get a bunch of epidemiologists on a call, you really have an opportunity to pick apart data elements and really discover some very interesting things. So not everything in this publication is directly applicable to like a clinical setting, but I think many of the concepts can be applied from a validation standpoint. Next slide, please. So I sort of was outlining challenges there, some of the opportunities that we have, the clinical quality measures that sort of are an indicator of clinical decision making. There are lots of opportunities there. They only look at essential hypertension. Maybe that's okay. They exclude pregnant individuals. So if we're trying to look at what blood pressure control sort of looks like, blood pressure management looks like in pregnant populations, we don't have those measures. They are being developed, thankfully, by the National Quality Forum right now. They have an initiative called Align Innovation. And early next year, we will have some measures looking at hypertension in both the pregnant and immediate postpartum period. And again, as future technologies come to light, the broader we need to be thinking about how do we incorporate these validated, acceptable blood pressure technologies into measures of blood pressure control. If we're not thinking about it now, or when these technologies first sort of come to light, it's like we have to wait years and years for them to actually get into practice. SMBP, many of you know, those values have been evolving over time, how they're being digested by the clinical quality measures. Right now, they don't say you have to use an average blood pressure, so that's problematic, but at least there's an essence of SMBP in those values. The PREVENT calculator, this is out. We think likely it's going to be involved in future hypertension guidelines. We know right now there are EHR installations that can't do an ASCVD risk calculation. And it's been years since that was the recommendation in the guidelines. So now is the time to be thinking about how do we incorporate the PREVENT calculator into an electronic health record so that it's ready to go when new guidelines come out. I'm going to skip ahead a little bit just for the sake of time. So I am a huge SMBP fan, and I heard Dr. Juracek, when he gave his opening remarks, highlight the fact that we have gaps reducing barriers to home blood pressure monitoring SMBP in clinical practice. And I do agree with that, but many of us have been working to close those gaps over the last number of years. There are a few things that have happened in the past 2 or so years that I want to make sure everyone knows about. One of the biggest barriers that I've heard from, can you go back, from clinicians, is that there's no place to capture an average blood pressure in the EHR. Well, there's something called the U.S. Core Data for Interoperability. Blood pressure control, we sort of advocated with a lowercase a and put comments in, public comments in supporting the use of average blood pressure in electronic health records. So soon in coming years, that will be a mandatory field that electronic health records will have to be able to capture. And Cardex is a standards effort that I encourage you to check out. I think this will really help streamline data transmission for SMBP as well. I'm going to end it there because I know we're over time, but I'll pass it over to you, Kate. Thank you.
Oh, thank you, Hillary. I'll let all our speakers come back on camera here, and I just want to kick off our discussion section by thanking all of our speakers. These were wonderful, wonderful presentations. Really, I think the whole day has been fantastic. And as we get into questions, I'm reflecting that, coming from the implementation side of things and working with clinicians and care teams, I see that many of the issues that we've discussed today are really not top of mind to them. They really do not have a lot of awareness into some of the questions that we're thinking about, trying to surface and trying to answer with further research. So I hope this group, in addition to really identifying research gaps, I hope we can also identify what is settled, and really kind of surface that and outline that and make it very clear to clinicians and care teams what best practices are, and work towards getting those things all incorporated into guidelines. And then some of us here on this call can really, I think, take that and work on the implementation side of things. But I know part of our charge today is really talking about those research gaps. So my first question, really to all the speakers, you all identified major gaps and opportunities. But if we had to push you on that single sort of low-hanging fruit, or that single highest priority for us to solve with further investigation that would really advance this field, what would it be? And maybe we can go in order of our speakers, starting with you, Marwa.
I'm going to say we should be implementing things we already know work. So focusing on the work that Tammy has done and others on this call have done is proper technique and education, and it is barriers within our own communities as clinicians, broadly defined, whether it's from community health workers all the way to physicians and other types of professionals. I worry that actually with more information, more new devices, more continuous, thresholds, all the things that I brought up, we're going to do worse because we haven't gotten the basics correct. And that's going to cause more problems in the future rather than solving any.
Yeah, keep it simple. I think there's a lot of value there. Rama, what about you?
Well, I talked about cuffless blood pressure technology and where it stands at present, but I'll try to answer your question more broadly than my talk. And, the unfortunate thing is in cuffless blood pressure measurement, there is no low-hanging fruit. Developing accurate cuffless blood pressure devices it's a super hard technical problem. And since the regulatory cleared cuffless devices only measure blood pressure changes, their validation requires inducing blood pressure changes. And this makes validation a hard problem as well. And so I would say, for the attendees of this workshop, that probably the single high priority item to address would be to develop a validation standard for cuffless devices with consensus from multiple groups. And I think that some of the people should have the technical knowledge and be impartial. Need to have both of those. And a validation standard, it would be important for two reasons. So one reason is to prevent inadequate devices from being used in patient care. And the other reason I think it's just as important is to foster the development of new technology that could successfully pass the validation standard.
That seems like a good tee up for Tammy.
Yeah, so I think, well, actually, I like what Mara was saying. I think, we can do a better job of using the tools that we have, but I also think I would love to make it easier for patients to provide us with home or out-of-office blood pressure measurements that are accurate. That is such an amazing tool. I mean, that's where most of our patients are spending their time, but especially in children, it's really hard to get good out-of-office blood pressure. We don't have enough devices. The kids don't really enjoy wearing them. It's hard for families to have to, if we're doing an ambulatory blood pressure monitoring test, they have to come to the clinic to get the device. They have to return it. They have to take off time. And we just don't make it easy for patients. And so I think a lot of our patients are not getting optimal care. So I think if we can come up with ways to make it easier to get out of office blood pressure measurements for all patients, and make sure we address some of those disparities with that, I think that would be really great. That would be where I think the priority should be.
And I'll just build off what Tammy just said. I totally agree. We need to make it easier. And one of the ways we can make it easier is by focusing on interoperability and standards. Because right now, all of our technical health IT tools, they all speak a different language, a proprietary language. And so when you try to transmit from one direction or the other, you have to translate between every unique system. And that poses its own set of challenges. So there are standards that exist and more standards need to be built. But I think focusing on interoperability helps us now for the tools that we have and helps us as we think forward, what tools are coming.
Just one comment on that before I know Kimberly wants to ask a question. I agree with you on the standards, Hillary, but I also have concerns about the pace at which this works. You've mentioned the USCDI, version 4 that will include ambulatory or average blood pressure. I'm not sure we know the implementation date of that yet. I think it's going to be 2027 or 2028. So
we don't know for sure, but
it's too slow. Yeah.
I think we can pressure. I think if everyone is pressuring EHR vendors to pre-certify on those data elements, I think we might be able to make some headway.
Thank you so much. I think my question actually follows that pretty well. Rama touched on the fact that cuffless blood pressure devices may not be, clinically ready. Once they are clinically ready, how do we see these devices being incorporated into clinical decision making? Is the first step, having these devices connect to EHRs? What's the first step in incorporating those into the clinical decision making?
There are many first steps that have to happen all at the same time, I think.
Well, as a clinician, I have to say, I'm a little worried about once we get all that information from patients, it's going to be a massive amount of data. And I don't know, I think that's going to be challenging to figure out what to do with it. And I also think things that are going to be challenging, just as a step back, when I get home blood pressure measurements, sometimes I'm not sure what to do with them because did they get a validated device? Is the cuff the right size? I can't tell you how many kids are sent to the ED for hypertensive crisis because they used a small cuff and they need a thigh cuff. Is it the right size cuff? Did they adhere to all of the different steps that you need to for various for accuracy? And I've been spending the last couple of years of my career working on accuracy. And so when we have now these cuffless devices where I think that there's even more chance for error with what I'm seeing, it's going to be challenging. Not only am I going to have a lot of numbers to look at, but I'm going to need to think about, all these different things that might have led to some error. So I think that maybe I'll speak for me. I think as a clinician, I don't keep up with the tech in the same way that some really tech-minded people do. And so I'm going to need some help as these things become more available to figure out how to interpret this information when patients are sending them to me.
I'd also add the patient perspective. So in the sleep world, there's a terminology of orthosomnia. So orthosomnia, so there's personal sleep tracking, right? The old Fitbit devices and wearable devices. And there are people who are now getting obsessed with the continuous information, and it's actually causing worse sleep and sleep quality, right? This is now a new phenomenon. And why I started with, like, let's make what we know better. Because I'm concerned from the patient perspective, not just the clinician and management. Like, think about all the EHR like alarms that are going to go off once this is now incorporated, but also for our patients, if they're continuously looking at their smartphones, you know, for their blood pressure output, just the way that now continuous glucose monitors are doing, and people are now getting obsessed with the concept of continuous glucose monitors. What is that going to look like for the blood pressure in people who potentially are going to get more and more obsessed? I mean, I think some people, some clinicians will also, you know, like to turn off for ABPM devices, like to hide and mask the numbers throughout the 24-hour period, so we're not always getting this burden of alerts and, you know, messages through the EHR, like, hey, my blood pressure at this minute was this, what do I do? And there might be nothing to do, right? So that's my other concern on the other side of what will all this data do for patients.
We'll need to be smart with all this data, there's no question. I saw a couple questions coming into the Q&A and the chat that were related to kind of the fundamental differences potentially between ABPM and home blood pressure monitoring. I think, Marwa, maybe your talk might have prompted some of these questions. So the idea that, are they fundamentally measuring different things, and how do we kind of approach that? I think, Tammy, you even posed a question related to in children, you know, seeing differences with ABPM because of the activity that might be associated with kids while they're receiving ABPM, and also some earlier data we saw today about you know, active adults maybe having, you know, differences in their ABPM. So any comments that you have there about sort of those fundamental differences between ABPM and home blood pressure monitoring?
Sure, I think this is Dr. Townsend in the Q&A and posed this. I fundamentally think they're different. They're measuring different things. I think, you know, as a clinician, I try to think which patient would benefit, in addition to what the guidelines say, but which benefit do I just need a 24-hour like snapshot on, right? And then I actually want to know, like, you know, is there something in their home environment? I know Dr. Brook will later address the environmental concerns, but is there something in their home environment that may be causing their blood pressure to be elevated, or maybe it's, you know, interactions, whatever it is. As opposed to sort of home blood pressure, where I'm trying to get a longer term perspective of what's going to do, and really trying to advise people on how to sort of, you know, modify maybe lifestyle modifications and interventions. Because that's, I think, more of a dialogue between the patient and their own information. So with unattended office blood pressure, I think of it as just home blood pressure, just in a different environmental context. And I actually think if the data, truly high quality data that I mentioned with in-person randomization does show that unattended potentially may be better than attended, then that's really an opportunity for new patient engagement and saying, let me teach you the proper technique while you're with me in the office, right? That addresses some of the barriers we already know there. It's like, I'm going to take the time to show you how to do this right while you're here in the office. You're going to practice by yourself. You can ask questions, right? And I want you to continue this in an outside environment. And this is how I'm going to use your data across these different environmental contexts. I think when you present it that way, you really can have an opportunity to use home blood pressure and office blood pressure in a way that's, you know, potentially the same. And I think that's what Dr. Townsend was thinking in sort of some of the questions that he posed.
So staying on the
Sorry. I was just going to add on that to Marwa's point. I actually make a big production about what I'm doing when I'm measuring blood pressure, so that they all understand. Because as soon as I walk in the room, I say, okay, I'm going to move you over here so that you're going to be situated in the right spot. So your arm's going to be positioned well. I make them move out of the chair. I measure their arm, and I talk about the cuff. So I make sure that, I make a big show of it, not for any other reason, but for education. Like, this is why I'm doing these things. And I want you to remember this next time you're at your primary care doctors, so that you can make sure you can remind them to do this way moving forward. So I think that that's super important.
And there's another question in the chat similar to this ABPM conversation. When we're comparing cuffless devices to ABPM to estimate that asleep blood pressure, it's potentially there's the difference in the cuffless blood pressure versus the ABPM output due to just the ABPM making the user aware that they are getting their measurement taken. And so how do we factor that into the validation of these cuffless devices? Is it, or actually I won't even provide any examples, just see what the group has to say about that.
I mean, I would say that you could compare them at the same time. When the cuff is inflating, if a patient doesn't have interarm differences, you could, test that and, both under the perturbation of the cuff inflation. But if you look at, Stephen had showed some data of a commercial device being tested independently under ABPM, a cuffless device. And the ABPM device showed the nighttime dip, but the cuffless device didn't. So, you would think it would be the other way around if the cuff device was, causing perturbing the patient. And, I just want to also add, and like one of the key points of what I was trying to say is that, if you see cuffless devices detecting the nighttime dip in the future, that could be just because the cuffless device takes the time of day. So if it's like 1 a.m., 2 a.m., 3 a.m., maybe it takes the accelerometer too and sees you're not moving and just takes, blood pressure 15% lower than daytime. And so those are the things we got to worry about with a cuffless device. It's taking a waveform measurement from a wearable, and it's taking like demographics and cuff for calibration. You have to think about, well, did the waveform help in the measurement or not? Because if it didn't, why would you wear it? You could just have the cuff for calibration and the demographics and put it in your smartphone and get some calculation out. And that's what I mean. There's no evidence to date that waveform is providing any added value. So,
And one thing to add on to that, for me, when I've been at a lot of these hypertension meetings, and I've seen that data that Stephen displayed, and there's been a lot of conversation about how to test these devices while we're sleeping. And ambulatory blood pressure monitors are never tested during sleep. They're never tested while supine. And so we're comparing a device that we don't even know how it performs in that position or in that condition. And we're assuming it's the reference standard, but we don't know if it performs the way we expect it to perform. So I think, to me, it's challenging me to think when I'm saying, can we make these the validation protocols align a little bit better? This makes me want to revisit how we do ambulatory blood pressure monitoring testing, because I think that'll help us inform things moving forward.
I think we may be at our time. I'm not sure, Paula, if we should hand it back to you or anything else right now.
I would like to invite the meeting chairs for some closing comments for day one.
Well, from my perspective, it's been a fabulous conversation. I know there's many more things we can discuss. I wanted to first say thank you to all the speakers. It's been a great day one. Please keep the engagement up, and we're going to try and collect all these questions as well so that we can use them moving forward for day two and some of the breakout sessions. Stephen, I know you're...
Yeah, just this is exceeded expectations. I came in with really a lot of excitement for today. The talks have been fabulous. The questions have been really wonderful and thought-provoking. I feel like we don't have enough time, and I kind of did expect that. So really excited to continue with the same level of passion and engagement tomorrow. And thank you all for joining today. And again, Paula, for all your leadership in organizing this. So.
Thank you all for a great day today, and see you tomorrow at 11 a.m. Bye-bye.
Yeah. Bye-bye.
Take care.
Recording stopped.
Rama made a great point. I don't know if Josh is still on or Antoine. Will we be able to save the chat?
You got chat saved.
I don't think I heard.
Oh, wonderful. Okay. And presumably the Q&A is saved as well.
Yes, the Q&A and chat is saved.
Okay, great. Perfect. Thank you so much. All right,
You're
all.
welcome. See you tomorrow.
See you
Thanks so
tomorrow.
much, Joshua, for all your efforts, and
No
Antoine.
problem.